guys, welcome back to our YouTube channel CDA Math. Today we're going to be talking about the mathematical concept of exact differential equations.
In order to understand more topics, make sure to like, subscribe to CDA Math and share and comment down below. Thank you.
Let's discuss differential equations. So a differential equation, it is an equation with an unknown function and the derivatives of it. It represents the relationship between the variable, the function of the variable and the rate at which that function is changing. Now, differential equations, it has many applications. It comes in engineering, biology, economics, etc. So it comes in different fields. There is order of the differential equation, which is the highest derivative present in that equation. And the degree, that is the power of that highest derivative, is the degree of the differential equation. Let's come to an example. So d square y by dx square plus 6 dy by dx plus 5 is equal to 0. Here our order, that is the highest derivative present, is 2. So our order is 2. And degree, that is the power of this derivative, is 1. That is why the degree of this differential equation is 1.
So now we're going to study what an ordinary differential equation is. An ordinary differential equation is a differential equation where there are derivatives with respect to only one independent variable. So what are independent and dependent variables? Let's take an example. dy by dx plus y is equal to 0. In this case, the dependent variable is y and the independent variable is x. So does anyone have any questions?
Ma'am,
Yes.
what is the difference between an ordinary differential equation and a partial differential equation?
Okay, so an ODE or an ordinary differential equation is one in which there is only one independent variable. Like in this case, x is the only independent variable. Now let's take an example for a partial differential equation. So dou z by dou x plus dou z by dou y equal to 0 is a partial differential equation where there are two independent variables x and y and one dependent variable z.
So now coming to what an exact differential equation is, it's basically a first order differential equation that is of the form n dx plus n dy is equal to 0, where dou m by dou y is equal to dou m by dou x. So if this is the case, then this is an exact differential equation. N and n are basically functions of x and y. So now coming to how we solve an exact differential equation. After we've checked that it is an exact differential equation, we basically integrate n with respect to x and we keep y terms constant, and we sum that with n dy, where we basically ignore all the x terms and we only integrate with respect to y. We'll see. That will be our solution for the exact differential equation. Okay, so in a lot of cases, your equation might not directly be exact, but you can convert it into an exact differential equation. So if we have an equation of the form mx plus ny does not equal to 0 and it is homogeneous, then you can make it exact by multiplying it with 1 by mx plus ny. And this will be your individual factor. And this will be rule 1 for making your equation an exact. Okay, so now coming to an example of rule 1. Here we can see that dou m by dou y does not equal to dou m by dou x, and it is a homogeneous differential equation. So we find mx plus ny, which is equal to x squared into y squared, which is not equal to 0. So that becomes an integrated factor. So we divide this entire equation by 1 by x squared into y squared, and we're left with this. And when we find dou m by dou y and dou m by dou x, we find out that both of them are equal and equal to minus 1 by y squared. So that means it is now exact. So then for the solution, we integrate the n term with respect to x and the n term with respect to y, leaving the x terms. So here that's why we have left this term out and we only consider 3 by y. And then when we integrate it, we get x by y minus 2 log x plus 3 log y is equal to c. Okay, so now coming to rule 2. So rule 2 is basically when you have an equation of the form f1, which is the function of x and y, into by dx, plus another function of x and y into x dy is equal to 0. So now we can make this exact when mx minus my does not equal to 0. So then we can make the integrating factor equal to 1 by mx minus my. And then you use the other rules for solving an exact differential equation. As when you multiply this equation with the integrating factor, your equation will become exact. Okay, so now let's take an example of rule 2. Here we have an equation of the form f of a function of x and y into y dx plus another function of x and y x into dy is equal to 0. So here we find dou m by dou y and dou n by dou x, which are not equal. So then we have to multiply with an integrating factor. Here rule 1 will not apply because it's not a homogeneous differential equation. So we multiply nx and ny and we subtract the two of them and we left with 2x square y square, which is not equal to 0. So our integrating factor becomes 1 by 2x square y square. And now we find dou n by dou y and dou n by dou x with the new equation, and we find them to be equal, which is equal to 1 by 2 minus 1 by 2x square y square, which is equal, so it's exact. Then after we follow the same step and we solve it, we integrate n with respect to x and we integrate the n term with respect to y, given x out of it is equal to c, and then we get the solution.
Another way to make differential equations exact is rule 3 and rule 4. In rule 3, the dou m by dou y as the partial differentiation of n minus dou n by dou x, which is the partial differentiation of n. If you whole divided it by n, you will get the function of x alone. And then your integrating factor will be e to the power integration of f of x dx. In rule 4, dou n by dou x minus dou n by dou y, you divide this by n, which is equal to the function of y alone. And the integrating factor will be e to the power integration of f of y dy. Now we'll understand how to use rule 4. So this is our question, and we will take n, which is our dx terms. Okay, so then this is dx square y to the power 4 plus 2xy, and n is our dy terms, which is 2x cubed y cubed minus x squared. Then we partially differentiate n with respect to y and n with respect to x. So then we get this. Clearly, dou m by dou y is not equal to dou n by dou x. Then we have to use rule 4, which is dou n by dou x minus dou n by dou y whole divided by n. So then you get this. When you solve this, you will get minus 6x square y cube minus 4x divided by 3x square y to the power 4 plus 2xy. Where we can take it common and we can cancel the numerator, cancel whatever common terms are there in the numerator and denominator, which we will get minus 2 by y. So here we will see that this is a function of y alone. That means our integrating factor is e to the power integration of our minus 2 by y dy. Okay, then we will get minus 2 log y, and this we can write it as 1 by y square because minus 2 will go up. So then it will be 1 by y square. Then we will rewrite our n and get dou m 1 by dou y, which is 6x square y, which minus 2x by y square, which is also equal to our dou n 1 by dou x. Then we will integrate our new n1 and n1 terms. So that is integration 3x square y square dx plus integration 2x by y dx. We have omitted the n because there are x terms in it. Then finally we get our answer x cube y square plus x square by y equals c.
So now moving on to rule 5. If we have an equation in this form where the constants are a, b, m, n, r, s, p and q, then we use rule 5. In rule 5, we have the integrating factor as x to the power h and y to the power k. By multiplying the integrating factor to the given equation, we will obtain the condition for exactness. Let us further understand by a question. Now, we have this question. Our first step is to check if the equation is in the form for which we can use rules. We know that this equation is in the form that I have previously mentioned. Now we will multiply the equation by our integrating factor. Both parts of the equation with our integrating factor x to the power h, y to the power k. After that, we will use the coefficients of dx to get n and the coefficients of dy to get n. In order to reach this position, we will open up the brackets and multiply. Now, we will do dou n by dou y, dou n by dou x by partial differentiation. Now, we take the assumption that dou n by dou y is equal to dou n by dou x. Hence, we can use x k plus 1, k plus 2, h plus 1 and h plus 2 and solve them simultaneously. By solving them simultaneously, we can get the values of h and k. Like in this case, we have got h is equal to 1 and k is equal to 2. We will use these h and k values and input them back into this m and n equation. By doing that, we will get these values for m and n and solve and then integrate n, where y is a constant, and n by omitting x. Since both the parts of the equation contain x, we will omit the x n term completely and only integrate the n term. This is the solution we get after integrating the m term. That's our final answer.